Good evening. The intention of creating this video is familiarizing with the OBS and OpenShot. That means it's a part of the faculty development program organized by RC Ramanujan College of Engineering, Ramanujan College, New Delhi. This program is sponsored by Ministry of Human Resource Development Group. So the sources used from the internet, there is no original material here. Everything is derived from the internet only. The purpose is only how I familiarized with using the how developing the e-content and creating e-videos for the education purpose. So for time being, I consider the topic that is main subject material science, in which the phase diagrams are very important concept is the phase diagrams. I'm going to discuss the phase diagrams. Phase diagrams are an important tool for the material technologies. Its diagram demarcates the region of existence of various phases. This is similar to the map which demarcates region based on the political, geographical, ecological criteria. Though the underlying of the phase diagram is much is a must for all the material scientists. The phase diagram are also referred as equilibrium phase diagrams. This implies that any microstructural information or light on the phase diagram is therefore convenient or not implied by the phase diagram. The fact that phase diagrams that represent microstructural level equilibrium is often not stressed upon. So broadly, two kinds of phase diagrams can be differentiated: those involving the time and those which do not involve time. So in this class, I shall deal with the phase diagrams not involved with time. That means those with composition as a variable, that is temperature as a function of the percentage of the given material, or if it is a pure component, it's a pressure versus temperature. Temperature composition diagrams are extensively used in the material science and will be considered in detail. Then time, temperature and transformation diagrams and continuous cooling transformation diagrams involve time. These diagrams are designed to overlay the microstructural information that is used for the heat treatment purpose. So that by the definition, component of the system, uh, independent chemical species it comprises of the system is include it can be elements, ions and compounds. You consider a system, binary system, copper and gold, where the elements are copper and coal. Ice water system, that means the component is water. It's a component. In the previous case, it's the elements. Then it need not be the elements and the thing, but also it can be ceramics. Say for example, Al2O3 and Cr2O3 system components, Al2O3 and Cr2O3. That is a system. So gaseous phase, liquid phase, and the solid phase. The mixtures. So here it may be homogeneous mixtures or heterogeneous mixtures. Homogeneous means it has a single phase. So what is a phase? Phase is anything which is physically distinct and chemically homogeneous. Mixtures. Say for example, it's the heterogeneous mass. It's a heterogeneous mass. Then what kind of phases exist? Based on the state, it can be gas, liquid, and based on the atomic order, amorphous, quasi-crystalline, and crystalline. Based on band structure, insulating, semiconducting, semi-metallic, metallic. Based on the property, para-electric, ferromagnetic, superconducting. Based on the stability, stable, metastable. Also, sometimes neutral. So, map demarcating the region of stability of various phases, or it's called a phase diagram. Or phase diagram is a map that gives the relation between the phases An equilibrium in a system as a function of temperature, pressure, and composition. The variables of thermodynamic aspect, the temperature, pressure, and the volume. So in kinetic with respect to time, composition variables means the component as well as a function of the composition. In a single component system, that means in here we used to call it as a unary system. The usual variables are temperature and pressure. In phase diagrams used in material science, the usual variables are temperature and composition. In the study of phase transformation kinetics, time, temperature, and transformation or continuous cooling transformation diagrams are used where the axis is temperature and the time as well as the transformation is involved in that. Then phase diagrams are an once again summary of the material. In continuation with the previous class, phase is anything which is physically distinct, chemically homogeneous, and mechanically separate. Phase diagrams are also called the equilibrium diagram. Equilibrium diagram. So the statement also implies that microconstants can be included in the phase diagram. Certain phases may be included in the phase diagram which are not strictly equilibrium phases, means that may be decomposed in the latter time. The variables on the phase diagram, where C is the number of components, P is the number of phases, F is the degrees of freedom. Based on the Gibbs equation, we can observe that P plus F equal to C plus 2. These are the variables. This is the Gibbs phase diagram. Then where F is the degrees of freedom, C plus 2 what we can control, P is the what the system controls. System decides how many phases to produce the given conditions. Can what we can control the number of the components added and the pressure and the temperature. So or you can remember like the Polish force equal to K plus 2 in another way. So Gibbs single component system or a unary system, unary phase diagrams. The advantage of the phase diagram is that, see for example, if we consider the by considering the phase diagram of a single component, um, compare iron, aluminum, beryllium, and magnesium. So the boiling points, if you consider the boiling points, which is the lightest material, the lightest material is the beryllium. Beryllium can, the latest material magnesium, the boiling point of the magnesium is much lower than the boiling point of the other components. Much lower than the boiling points of the other components. Even though it's lighter, it can't be used in the aircraft application because it sublimes at higher, uh, at lower pressures. The temperature of vaporization sublimation is also very low. So easy, it evaporates very easily. That's why it can find the application in the aerospace industry. Aluminum having a reasonably high boiling point, therefore the high melting point. Therefore, it is suitable for the aircraft application. Beryllium carcinogen. Not only that, magnesium is also pyrotropic in nature. So here, in the single component, what are the various phases present in the, how you can apply the Gibbs phase rule, we will see in the, so for any given C, this is the phase diagram of a iron. So at nearly 910 degrees centigrade, so iron transforms to from BCC to FCC, and then FCC to delta BCC, then again it will go to the liquid phase, then at nearly 3000 degrees it gives to the vaporization. So this gives the temperature and pressure. This is a pure component system. For any pure component where the degrees of freedom equal to 2. So the line, at any line on here, the number of the degrees of freedom equal to 1, where at the triple point that is located in the both sides, both the things, that is where the degrees of freedom equal to 0. Degrees of freedom equal to the 0. See here, phase is up to 1535 degrees centigrade. The iron remains as a solid, but when it is heated to a temperature above 910 degrees centigrade, alpha iron transforms into gamma iron. That means the crystal structure is different. That's why a new phase is gamma phase. So again, gamma phase is transformed into the delta phase. Again, it is a BCC structure. At high pressures and the low temperatures, the alpha BCC again transform into unstable thing HCP, hexagonally closed back the structure. So from when this gamma dissociates into the BCC and HCP, that there is a point that is called the triple point. This is the importance of the single phase diagram. Thank you.